É que a gente falou, depois tem que dar uma... Colocar aqui mais para... Tá naquela posição 1? Tá, depois eu vou enquadrar mais para baixo aqui com ele. Que eu acho que ele falou que ele vai ficar mais aqui embaixo. Then you prefer to stay here in the bottom, right? All right. The microphone is here, can you see? We managed to put that on the table.
Over here, probably.
It should work.
Working here?
Yeah,
Working.
He's will start the streaming now just to test the sound and everything. He was collecting some noise. Sure. Okay, pode ir. Going? All right, so hello everyone. If there is somebody watching, we start in a few minutes with the lecture from Professor Dr. Donny Orejon from Edinburgh University. There you go. Thank you. Ah, beleza.
Sounds very good.
There you go. Perfeito.
Perfeito, perfeito.
Talvez tenha sido aqui. Eu acho que ele mexendo ali estava fazendo, mas eu acho que tá tranquilo. Tá pra ouvir bem. Não, não atrapalhou não, ficou ótimo. Ficou ótimo. Pessoal. E grave também. For water, you have it. Okay. Wait a few minutes for people to arrive.
No rush.
Did you work with Yes?
With Takata?
Yeah,
Of course.
you haven't been here.
Yes.
When?
Visiting us. I think they told us 2018.
2018. When I left him.
It's a nickname.
Yasuyuki Takata.
Ah, Yasuyuki.
He
Yes.
likes people to call him Yas. Of course, I was in his lab for 5 years when I was in Japan. 3 years postdoc and 2 years so most of my work that I did in Japan is.
Enjoyed in Japan?
So sad I'm in Edinburgh now.
Yes, the secretary to make a coffee for a water here. You can see it work.
Please my water
It worked well.
there is alcohol.
Now she just said there she has. There you go. Thank you. Hi everyone. I think you're already aware we are also streaming this lecture via YouTube. So just a quick introduction. I'm Arthur Oliveira, assistant professor here at the University of São Paulo, São Carlos School of Engineering. And we are receiving Dr. Danny Orejon from the University of Edinburgh as a visiting professor here at São Carlos School of Engineering, who is presenting his lecture on turning droplet-surface interactions via function on grafting and opportunities for evaporation and condensation phase change. Just a quick bio for Danny. I had to write it down. It's an impressive biography. He's a bachelor in chemical engineering from University of Sevilla, 1-year graduate research assistant at the energy systems at the University of Edinburgh, PhD on fundamentals of evaporation phase change at the Droplet-Scale Institute of Materials and Processes at the University of Edinburgh as well in the 2013. He joined the Carbon Neutral Energy Research EESC at Kyushu University in Japan as a postdoctoral fellow in 2013, then assistant professor in 2016. When he shifted towards the investigation on condensation heat transfer. 2019, then he joined the Institute of Multiscale Thermofluids of the University of Edinburgh as a lecturer, and in 2022, he was promoted as senior lecturer. Also, he holds a visiting associate professor position at EESC in Kyushu University since 2019, now as a visiting professor here at São Carlos School of Engineering at the University of São Paulo, Brazil. And this year, he's a fellow at the Higher Education Academy, got the Young and Early Career Scientist Kakenhi Award, I forgot to ask how to pronounce, Kakenhi Award twice, in 2016, 2018, and has received a Royal Society Research Grant in 2020, and the University Strategic Collaboration Award between the University of Edinburgh and University of Rice, 2023. He also takes part of the SciSpace Microgravity Application Promotion Program from the Europe Space Agency since 2020 to 2022. So I'm very happy to receive Danny here at the University of São Paulo. He's already lecturing this course for the postgrad school, and now this talk on his research, which certainly has a lot to teach us on his field. Danny, thank you again for your presentation, for your staying here in Brazil. The place is yours. Thank you.
Thank you very much, Arthur, for the nice introduction, and thank you everybody for having me here, to all the admin at the university here in São Paulo, School of Engineering, São Carlos School of Engineering, and for everybody to be so welcoming. So I think Arthur has done a great job. I have this slide prepared to give you a little briefing of my background so far since I started my undergraduate career at the University of Seville, all the way until I am now. So as introduced by Arthur, the talk today is going to be on droplet surface interactions, and this is quite affine and quite similar to the course that I have been giving, or I am still giving during these weeks to some of the postgraduate students that are sitting, some of you here, related to heat and mass transfer at the nanoscale, at the micro and nanoscale, including both evaporation, condensation, and different applications. So I think some of the postgraduate students here, they are already some sort of experts on wetting. They have seen some of the fundamentals here, so probably they should be able also to give a little bit of part of this talk if I were not here. So to start with, this is the index of the presentation today. So we have introduction and motivation for this research. I will introduce how we are actually fabricating these surfaces, how we can try to tune the interactions between, I say droplets, but also works for liquids, okay, between liquids and solid surfaces. And I'm going to introduce two of the topics that are one of them on evaporation phase change, and the other one in the opposite phenomena, that is condensation. So as you can see here, a little bit of quite complete. All this work has been done by my student, Anna. Is now in her third year of PhD and is trying to wrap up now the condensation part. So very complete topic from fabrication to the different sort of fundamentals of phase change towards finding some applications here. So if we start with the introduction and the motivation, why are we looking into drops? As you guys know, drops are everywhere, right? Since we wake up in the morning, there is some dew drops on the grass, spider web, in the bar when we are having a beer, because the beer is very cold, right? The glass temperature drops below the dew temperature, and once that happens, condensation takes place, molecules of the vapor turn into liquid, and form these discrete drops around. Although today I'm going to just talk mainly about the fundamentals, mass transfer, evaporation, condensation, all these phenomena, phase change encompasses heat transfer as well. When a fluid evaporates, removes heat from the surface. When a fluid condenses, adds heat for the surface. This is why when I went to Arthur's house to have a beer the other day, he gave me actually a very nice insulating glass where you couldn't see any drops condensing on the glass because we wanted to keep the beer, the temperature cold. So condensation for our beer is actually undesirable, right? There are other processes, a little bit more industrial, like distillation of whiskey. Condensation takes place here at the top. And just a fun fact about, because I'm in Scotland, fun fact about whiskey, the taste, the final taste of the whiskey depends a lot sometimes on what is the material of the condenser, whether we have copper or other material, the whiskey might taste different. And because I spent 5 years in Japan, I always like to put a picture of an onsen. That's where I spend most of the time observing droplets, how they kind of form, nucleate, and kind of condense somewhere else. However, we as scientists, we don't get paid to basically just observe droplets for fun. We need to look into some specific applications where we can actually play a role, right? To try to make use of our fundamentals, our understanding of phase change to improve some of the applications. As I mentioned earlier, phase change encompasses heat and mass transfer. So here you can see, for example, an energy flow of USA in this particular case. On the left-hand side, we have here all the different inputs of energy that we have in our grid, from petroleum to coal, natural gas. And on the right-hand side here, you can actually see it's not working very well. You can actually see the different energy rejected and the actual energy that we use. So from all the energy that we are putting in our into energy sector system, only 33% is used, 67% is just rejected as heat. So if we look into different applications here, for example, electricity generation, you can see that around 64% of the electricity, the energy we put into the system is just rejected as heat. Industrial sectors also, they have almost 50% of the energy rejected. Transportation sector, almost 80%. And this is not just in USA, it also happens in UK. You can see similar numbers, but it also happens in Brazil as well, right? So this is the energy map in Brazil. I think regarding electricity generation, here you have one of the lowest energy rejected, probably because a lot of your energy is coming from hydroelectric power that doesn't consume CO2, and that energy is well transferred into the electricity grid without much losses. So these are kind of three sectors that we can look at and try to look for applications where our phase changes processes may play a role. And some of the applications are, for example, for the cooling of IT data centers. Currently, most of the IT data centers are cooled by either air conditioning units or by liquid cooling single phase that typically has low heat transfer. And currently, IT data centers right now, almost 2% of the energy produced in the world is going to cool down IT data centers. And as we know that we are even using more servers and more servers every time, probably that requirement will even increase. So if we are able to implement phase change instead of having single phase, we should be able to make more efficient the cooling of IT data centers with the savings in CO2. Transportation sector, cars, either the engine is also cooled down by single phase. If we are able to implement phase change, we should be able to also make all the cooling system of the cars much smaller. If it's much smaller, means less weight, so we can run our car for more miles with the same fuel. Electricity generation, very important. Currently, up to around 60%, 50-60% of the energy produced in the world is actually produced by 5 coal power plants. So it's a lot, not here in Brazil, but when you take into the overall picture. So there is this study, for example, points out that if we are able to halve the working pressure of our condenser, if we are able to implement a more efficient condensation process within our condensers, we should be able to increase the overall efficiency up to 1 or 1.5%. That again is very small, right? But accounting that 60% of the energy is produced via this technology, this means huge energy and huge CO2 savings overall. So also solar evaporators are some of the kind of applications that we can look at, make use of the energy of the sun to try to make processes more efficient, to try to make drinkable water easier. And as you can see here, most of these technologies actually, they align with the Sustainable Development Goals from the United Nations in terms of energy affordable for everybody, as well as clean water and sanitation. So given the motivation, we now go into give a little bit of details on the surfaces that we are working with, and also a little bit on the fundamentals of what are the different interactions between liquids and solid surfaces that I think some of you guys here will be able to present very well without me. So when we put a droplet on a solid surface, a droplet will achieve certain shape, and the shape of the droplet is depending on what is the wettability of our surface. We are talking now here only about the smooth surfaces. We are not going to complicate the story with the structures. When we have structures, we have different wetting regimes. But just for the smooth surface, a droplet will achieve a contact angle. We call it equilibrium contact angle, and it's going to depend on the different interactions between the solid gas, solid liquid, and the liquid gas. And these interactions are empowered by the wettability of the surface, the chemical properties of the surface, as well as the nature of the liquid. As you guys know, there are liquids that, when you put them on a surface, they are more spherical. There are other liquids like organic solvents, ethanol, acetone, that they wet more, right? So give different scenarios. And these are the typical scenarios that you can find. Complete wetting, when the droplet just spreads. Partial wetting, when the droplet achieves a finite contact angle, but this contact angle is below 90 degrees. And then we have the partial non-wetting, when our contact angle is actually higher than 90. And we typically refer to these surfaces like hydrophobic. Hydrophobic comes from the Greek. Hydro means water, phobic means hate. So it's clear that this droplet is kind of hating the surface, doesn't want to be there. Hydrophilic, here means hydro, again water, philic means like. So So this is why this droplet actually likes to maximize the interaction, maximize the surface area and the interaction with the surface. So typically, hydrophilic surfaces, they have quite high adhesion to the surface, but we actually want to look for the opposite. We want that our droplets have low adhesion to the surface. Above all, when we want to empower the so-called dropwise condensation, I will give a little bit this later, but when we want to empower dropwise condensation, what we want to have is a hydrophobic surface. Most of the surfaces that are out there, like metals, that are not man-made, or they are not like organic like plants. So metals, rocks, most of these surfaces are actually hydrophilic. They like to be, water likes to be on those surfaces. But for many applications, we actually want to empower the opposite behavior. We want them to be hydrophobic. So in order to do so, my student and I, we look into some easy techniques to try to change the wettability of our surfaces by 1 or 2 steps fabrication procedure. So we look into this work from Professor Stefan Hart in Germany, at Darmstadt, and we start to look into the different parameters that they studied, and my students start to do some functionalization of the surface, and we realize actually that we can just move from step 3 all the way to our low hysteresis or very low adhesion surface, just skipping 2 or 3 of the steps that you see there. So the actual fabrication parameter consists on we first clean the surface with some organic solvent. One of the important things is to bring the surface and to apply oxygen plasma. We apply the silicone oil. This is a normal silicone oil. It is environmentally friendly. It is readily available, no toxic. And then we just put it on a heating plate and we bake it at 200, 300 degrees for different times. And we take our surfaces in order to be able to characterize what is the interaction between the liquid and the surface. We take them in a goniometer where we can actually image nicely the interactions between the surface and the droplet. This is our original surface, hydrophilic, the droplet likes to spread on the surface. Whereas after just one layer, one application, one step of the coating, we can have a hydrophobic surface with a nice round shape that you can see here even clearer. These surfaces are sort of liquid-like because of the properties of the silicone oil, but you can see here that there is no sort of oil remaining on the droplet. Besides the wettability characterization, is also very important for us to characterize other parameters. And so we use AFM. This is working very slow, sorry. So we use AFM to characterize the roughness. You can see everything is in the order of nanometers, very, very, very smooth. We use also force measurements to characterize what is the thickness of our coating. This is also very important because it tells us how much material, how much oil we need to use, right? Sometimes we want to be very efficient on that because the more we use, the more money we'll have to spend if we scale the technique. But and tell us basically the thickness also for heat transfer. We don't want to have very thick films because they act as resistance. So we also want to minimize the thickness of those films. And these ones are in the order of 100 less, in the order of a micrometer or less. So quite small. So In the previous work that was done in Germany, they only used one single type of silicone oil, and they just utilized one single fabrication procedure. And they were able to get contact angles in the order of around 20 degrees of contact angle hysteresis, sorry. But my student Anam actually looked into different properties. She looked into the different viscosity of the oils. Silicone oils, we can find them in many ranges of viscosities, between 0.65 centistokes, so very little viscose, all the way to 1,000, even much higher than that. She utilized different deposition methods as well. I mentioned to you earlier, the deposition method is going to tell us how much oil we are putting on the surface, as an example. Different volumes of the oil, and also she studied different numbers of layers. I'm not going to go much into detail today, but we did not look much into the 1,000 centistoke oil, because the deposition of the oil actually is also a kind of phase change process, and it involves many mechanisms like the wetting, evaporation, and it needs to be well controlled. So I will not be talking to the 1,000 centistoke today, just 5, 20, and 100. And we characterize these surfaces in terms of contact angle hysteresis. Contact angle hysteresis is a sort of metric that tells us how a surface, how a droplet will adhere to the surface. Okay? Just as a reminder, we are looking always for droplets that are very mobile. So the lower the contact angle hysteresis, the better. So when we look into wettability, so how hydrophobic my surfaces are, right? Independently of the type of oil, 5, 20, or 100 centistokes, independently of that, all my surfaces are hydrophobic. So this is a good sign that my procedure actually works, and I can transform a surface that was intrinsically hydrophilic into a hydrophobic just with one step. In the case of one layer, few more steps if I am adding more layers, right? When we look into the hysteresis, this is the contact angle hysteresis I mentioned to you before. We are also reporting on the sliding angle. Just as a metric for you guys, the higher, the worse, okay? And the lower, the better. So you can see here how for most of the cases, as I increase the number of layers, about all for low viscosity oils, I'm able to decrease the contact angle hysteresis or the sliding angle. This is because when I have low viscosity oils, sometimes my procedure leaves the surface with patches. So the coating, the coverage of the surface is not completely homogeneous. Then I need to put another layer to be able to cover that, and sometimes even another one, until I get a nice homogeneous coating, like in this case, and I get very low hysteresis. But I think I want to call your attention, guys, to this diagram here on the right. So you can see here, just for one single layer of 100 centistoke oil, for one single step, we were able to have contact angle hysteresis lower than 1 degree. This is at least tenfold smaller than what was found before, because of our optimization procedure. So this is a sort of recap on how the different parameters actually affect the contact angle hysteresis. And this is the recipe that we propose here. So we propose that if we have a low viscosity oil, these are basically the methodologies that we want people to follow. So to get the lowest hysteresis possible, to get the surfaces where my droplet is very mobile. Whereas for high viscosity oils, this is our recipe: deep coating, low volume, just one number of layers, enough to give me one of the lowest hysteresis out there, and also gives we want to have low roughness. So again, it was twofold decrease in contact angle hysteresis after they have done many steps, but if they don't clean the surface, we actually got even 10 times better results than the ones they were reporting previously. And then we realize, as you can see here, depending on my fabrication procedure, actually I can empower different interactions with the surface, right? I can have different contact angle hysteresis. So this is what we exploit in the next topic. We try to use different fabrication parameters to see whether we can control how a droplet will evaporate on a solid surface. That is very important for many different applications. So this is the conclusions of this part. One is the fabrication, and we are able to tune the contact angle hysteresis. We go now into tuning the droplet evaporation. So just as a brief example, so normally when a droplet evaporates, as I mentioned before, encompasses those heat and mass transfer. And those are some of the things that we can observe. And if we put particles, we can have the so-called coffee ring stain. As simple as it looks, a droplet is not so simple. And when you look into the different mechanisms and the different kind of fundamentals that are taking place at different interface and in different phases, you can see that it's a very, very complex phenomenon, right? So we try normally to decouple things to try to understand the fundamentals better. In the case of evaporation, there are many applications out there. Inkjet printing, most of us have a printer at home where basically you have a droplet. The printer just impinges droplets that have a solvent, have particles with different colors, and they go into the paper, they evaporate, and you get the print out. They are also used for heat transfer. Microfluidics also, we use droplets in order to try to minimize the amount of volume that we are using. For example, we take blood from a patient and we don't want to drain the patient, we want to minimize how much blood we use for each of the assays, right? And it has been proposed to study whether a person is healthy or not. So depending on how it evaporates, depending on the patterns that live, you can see this one here is very regular. This is the one for a healthy person. And whereas these other ones, they have like some disease. So as you can see here, droplet drying have many different applications. Here are the main modes of evaporation of a droplet. So when a droplet is on a solid surface, if the interactions between the droplet and the solid surface are very strong, my droplet is going to evaporate in what we call the constant contact radius mode, where the contact line is pinned and the contact angle decreases to attain for evaporation. Whereas if my surface the droplet is very mobile, contact line can depend. What you see here is that my radius actually decreases in time, whereas my contact angle is constant and the droplet evaporates like this. Two different mechanisms that at the end of the day, they are going to play a role on heat transfer and they can play a role on how particles deposit as well for printing. Then we have the mixed mode, typically appearing at the end of evaporation, both the angle and the radius decrease in time, and in specific conditions, stick slip mode, but we are not going to look much into this today. So, droplet evaporation. This is the typical behavior that a droplet undergoes when it evaporates on a hydrophilic surface. Okay, this is a silicon wafer, and typically it evaporates with a pinned contact line for 40–50% of the evaporation, and then the contact radius decreases. This is the benchmark kind of behavior on a hydrophilic surface. Whereas on a hydrophobic surface, remember, the contact line is very mobile and the droplet is just gonna shrink, keeping a constant contact angle, whereas my contact radius decreases. So in this surface here, hydrophilic contact angle hysteresis is very high. In my hydrophobic surface, contact angle hysteresis is very low. And remember that the functionalization that I presented earlier, depending on my fabrication parameters, I actually can empower more hysteresis or less hysteresis. So my student Anna, she prepared all these many type of surfaces. This is for the low viscosity oil, medium viscosity oil, high viscosity oil, and this is the range of hysteresis that we were able to achieve. From very high hysteresis, more than 20 degrees, all the way to less than 1 degree. So this is what we wanted to look at. And if we look into the coatings or the procedure that gives kind of one of the highest hysteresis, you can see here at the top that in many occasions my contact line remains sort of pinned and then evaporation occurs. A little bit similar of what was happening on the hydrophilic surface, on the hydrophilic silicone. The same here for this viscosity oil. Also, I have a little bit of pinning and then my contact line receding. So I can kind of put a little bit of guidelines and I can say that if I have more volume of oil and more layers, my contact line is a little bit more mobile. And as you see there, the more layers, the less pinning. So just with the same viscosity oil, I can play a little bit on the different behaviors. I can empower or I can make the droplet to pin a little bit more. When I look into the 20 centistoves, remember medium viscosity oil, it was also providing us with a medium contact angle hysteresis. And also here again, I think we are actually shortening a little bit what is this initial constant contact radius mode, while my droplet evaporates then in the constant contact angle mode. And one of the most interesting ones, again, 100 centistokes for one layer, actually, so the one that just needs one step. And you can see here that I am completely suppressing any initial pinning, and my droplet just evaporates continuously in the constant contact angle mode almost until the end of evaporation. So just this surface, one layer of the coating, is even better than Teflon that has been used and utilized for many years, and we actually have at home in our pans for cooking, right? So a little bit for a more fair comparison and to point out that depending on our fabrication procedure, we can range behaviors between hydrophobic and hydrophilic. Here are some representative cases where we have in red is actually Teflon, whereas in gray here is silicone. And you can see here that most or all of our results can be actually similar to Teflon or in between. We are not quite all the way to silicone because of the high contact angles of my coating, but you can see that qualitatively the behavior is very similar to that of silicone for this case where the contact angle hysteresis is quite high. And the same for the contact line. The contact line of our droplet also, all the results lie in between Teflon and silicone. So again, depending on my fabrication procedure, I can actually lay closer to silicone, closer to the hydrophilic benchmark behavior or closer to the hydrophobic, even better than Teflon. This one is an analysis. So remember, I mentioned to you typically we have constant contact radius mode, constant contact angle mode when the angle remains constant, and at the very end, mixed evaporation. So this graph here, it takes all those samples that I have represented before in the previous slide, and is just giving me what is the percentage of time that those droplets spend in each of the modes. And a little bit for simplicity, these were the ones for 100 centistoke oil. All experiments for 100, sorry, this is for 20, but these two are for 100. P stands for 100. And you can see here that my behaviors for all these three substrates, they are very similar to the one on Teflon. We have similar range of the constant contact angle mode and similar range of the mixed mode. We are just missing this small constant contact radius mode, but ideally for what we want, it's even better that we don't have this constant contact radius mode. This means that our surfaces have lower hysteresis, my droplet and my contact line is able to move more freely over the surface. And if I take this other experiment, this other type of fabrication procedure, we can see here that we are also getting quite high initial CCR, not as much as on silicon, but also similar, a little bit of bigger CCA and similar mixed mode. So again, with same type of procedure, just varying the different parameters that we are playing with when we functionalize the surface, we can actually move from a droplet that evaporates almost like on a hydrophilic surface, all the way to a droplet that evaporates with free contact line, even better than on the hydrophobic surface. So demonstrated, we are able to sort of tune based on the parameters whether we have more CCA, more CCR, or more mixed mode, depending on our fabrication parameters. And one of the main points also is basically that we can actually have a droplet that is very mobile on the surface because of the nice low addition properties of the surface. So this was related evaporation, and don't worry guys, for condensation I don't have so much. There is not so much data, not so much results right now. My student Anami is now back. She actually spent like a month, 2 months back in Pakistan. She got married, and I gave her a couple of months off. And now she's back to business, trying to do more experiments, trying to wrap up this condensation part. But I think, hopefully, as for now, I have conveyed that depending on my fabrication parameter, I can actually have different interactions between the droplets and the surfaces, right? And this is what we want to empower for condensation. We want to be able to also tune what is my, not the condensation behavior. We want to always move into dropwise condensation, but presumably we can actually tune the size of the droplets that are shedding from the surface. So presumably for lower hysteresis surfaces, small droplets will be able to move from the surface if my surface is vertical, whereas for high hysteresis, the droplets would like to stay more on the surface. They need to grow bigger for them to shed. So we look a little bit into condensation. As you can see here, it looks like a droplet on a surface. It looks very similar to evaporation. Somebody might think that it's just the opposite phenomena, but there are many other mechanisms taking place. So myself, I did my PhD on evaporation. I did my postdoc sort of in condensation. For me, my postdoc was like kind of another PhD because although evaporation and condensation share some similarities, but it's a completely different phenomena. And here are the main factors affecting wettability. Hydrophilicity, if the surface, if the water likes the surface, typically I move into what is called film-wise condensation. If my surface is hydrophobic or superhydrophobic, I have drop-wise condensation. Don't remember if I have here, but just for your record, guys, drop-wise condensation has much better heat transfer efficiency than film-wise condensation. Okay, so typically we are looking forward to develop surfaces that can empower drop-wise condensation on my surfaces, so to improve the heat transfer efficiency. Structural effects can also give me different condensation behavior. The type of fluid, water, organic solvent. Water on a hydrophobic surface likes to be round. I don't know if you guys have played with ethanol, with some organic solvents. When you put on a surface, it kind of completely spreads because they have very low surface tension, right? So it also can have different condensation mechanisms, drop-wise, field-wise. The presence of non-condensable gases also play a role on the dynamics of condensation. But I think today is just about wettability, is just about the surfaces that we have developed. Just for your record here, very quick, hydrophilic surface, main condensation behavior, field-wise condensation. Hydrophobic surface, drop-wise condensation, as long as my surface doesn't have very high contact angle hysteresis. If the surface has very high contact angle hysteresis, even if it's hydrophobic, you may get film-wise condensation. And then on superhydrophobic ones, you can empower drop-wise condensation, but also what is so-called coalescence-induced droplet jumping. This means when two droplets coalesce, they actually are able to jump from the surface because of the excess of energy released. So my student Anna, in her third kind of part of her PhD, designed this setup, plexiglass chamber, Peltier stage. You can see all the details here with some lights. We use a lens, zoom lens, for a spatial field of view of around 1 millimeter to be able to observe micrometer droplets, as well as a little bit more wider to have the holistic view of the surface and the condensation process. So we couple both. We have a copper block here, Peltier stage, with an additional polymer block to try to avoid condensation around. And then we stick our sample with a double-side copper tape. And we are trying also to put some cuvettes here to try to measure the condensate, although that is not, those measurements are not very precise today. She needs to work a little bit more on this. But I think the takeaway from today's talk, again, is related to the interactions between droplets and surfaces. So this is one of the coatings, one of the fabrication procedures that gave the highest of the contact angle hysteresis. So where we expect that the droplets are going to interact the most with the surface. And as you can see here, droplets grow, and they need to be almost as big as a millimeter to be able to shed from the surface. Whereas on my lowest of the contact angle hysteresis fabrication procedures, you can see here that there are droplets already as small as few hundreds of micrometers that are able to shed from the surface. And again, this is because the different fabrication procedure, although it's the same silicone oil, right? But the silicone oil has different viscosity and has been fabricated differently, empowers the same wettability, but different contact angle hysteresis, different interactions. Sometimes, well, most of the time, this is not good enough, right? We need to provide some quantification. So my student, Anam, she actually measured the size of the droplets in time for almost every 5-10 minutes. And you can see here, this is how we typically represent the droplet population on a solid surface. This is the droplet size distribution that represent how many droplets of a specific size. And this, when you represent it in a log scale, this representation is always linear. If you look at the theory, it's always linear, okay? It's a characteristic property of condensation behavior. But I think the most interesting point and the takeaway point here that I have mentioned earlier is that if I look at my experiments on my surface with high contact angle hysteresis, my droplets need to be as big as 1 millimeter in diameter or 500 microns in radius for the droplet to be able to shed by gravity, whereas for my lowest of the hysteresis, droplets as small as 300 micrometers are able, in radius, 600 micrometers in diameter, are able to shed from the surface. And this is important because for droplet condensation, also, the smaller the droplets shedding from the surface, the better the heat transfer. Okay? I'm not demonstrating this here, but you can read a little bit of the literature and you are going to find that widely accepted statement. Okay, so this is what we are trying to look for. Small droplets shedding from the surface. It was the same wettability, just varying on the contact angle hysteresis. So this kind of concludes my talk. This is the final conclusion for the condensation part. So again, depending on the fabrication procedure, different hysteresis, different droplet size distribution, smaller droplets can even almost be half of the size of the high hysteresis one. So before I finish, and you guys can ask me any questions, I just wanted to basically thank all of you for attending here, the Sao Carlos School of Engineering for having me here, of course, Arthur, CAPES also for sponsoring my stay here during the 2-3 weeks, and all the students for attending the course that I am giving. My university, as well as the Institute of Multiscale Thermofluids I belong, ThermaSmart, that also help a lot. Some of the founders that have taken part a little bit on this project, the Higher Education Commission of Pakistan, that is actually funding my PhD student, Anam. A strategic collaboration award between Edinburgh and Rice that is allowing us also to move one step further, and we are also looking into using our coatings with the technique at Rice to make pattern wettability surfaces. All the people that actually was involved in this project, but especially to Anam. She's the one that took the most part on the fabrication procedure, the condensation procedure, as well as the fabrication of the surfaces for evaporation and the characterization with AFM on the roughness and the thickness. While Astrid, she was actually a master's student doing a project with me at Edinburgh University. She did all the experiments on evaporation, and she's the first author on one of the publications. And of course, I wanted to give thanks to that guy there for being so kind, having me here, taking me around, and for all his help so far. So with this, I would like to finish, and any questions are welcome. Thank you.
Danny, thank you very much. As always, amazing talk, amazing research. Thank you. I open the section for questions if anybody here has one. Because I have some, of course.
I have one.
Okay, so please, Deborah.
Okay. Well, first, congratulations on your talk. Very interesting.
Thank you, Deborah.
About the durability of the surfaces, have you investigated aging effects or something like that?
Not for a very long time, because you know there is need for quite manpower to do those type of tests. We applied some for the first part on the wettability bottle. We did apply some different tests to try to, but not like much in time. We did like different cycles. And for example, for some kind of mechanical test, vibrations, we were able to apply that for quite a long time without losing much the properties. We also did immersion in ethanol. If it's just immersion, also there is not much change. So what we did is we immerse the sample, we wait for 30 minutes, we take it outside, immerse it again. So up to 20 cycles doing that. So there are several tests that we actually did for these specific surfaces that are on the paper. For steam condensation, we did not get very good results though. So one of the potential applications would be basically for steam cycles. For steam condensation, we found that the hysteresis abutol, when we are talking about the low hysteresis one, it was going up not more than 10 degrees, but still not bad, keeping sort of hydrophobic wettability. But still, those tests for fundamental scale are quite okay, but we know that they are not enough for the practical application. So definitely, it's a kind of topic of research that we need to kind of, all of us as engineers, we should kind of always try to make it kind of extend longer, right? Because the applicability is a big issue. Excellent question, Deborah.
Thank you. I have another question.
Please.
Of course.
No, please.
About the patched surfaces that you mentioned for the low viscosity oil, I guess. Wouldn't it be interesting, for example, for boiling experiments or something like that? Because maybe not for condensation, but when we see boiling, maybe the mixed wettability or
Very good question, Deborah. I think pattern wettability for boiling is one of the kind of topics that we have tried to introduce and convey to the students within the course. I do agree, many reports study that combination of hydrophilic and hydrophobic enhances the boiling heat transfer. The only thing here, so I will say that maybe we will get, with this technique, we will be getting maybe a little bit of the opposite effect. I will say that we will get more hydrophobic regions than hydrophilic. So typically you want to have very small regions, kind of spots of hydrophobic, just to induce the nucleation, but to avoid sort of dry out, right, and to have more wettability to kind of re-wet the surface. Another drawback that I may see now is also that because this process is done by evaporation, right, but baking at very high temperatures, I think the position and the size of those spots will be very difficult to control, right? And in occasions, you might have one spot here, one there, different sizes as well. So that is not going to allow you to have some sort of repeatable or to actually even optimize, right? What will be the size between the spots or the size of the same spots. Also, presumably, because they are not so good for condensation, I might not put my hand on the fire that are going to be great for boiling, because boiling, I will say, probably is even much harsh environment than condensation with steam, right?
Okay.
Also, a very good question.
Thank you.
I might have one more.
If that's it. Somebody has a question?
Arlindo had a question here.
No, actually, it was the same question posed by Professor Deborah about the durability of the coating, but that was it. Yeah.
Actually, that's always an issue when you talk about durability, when you talk about coating. That's a good question. Cristiano, please.
Please, Cristiano.
What's about the effect of the base material, like aluminum, steel, and the base material roughness?
So it does play a role. So in the supplementary information on the first part, we did the work with copper, and I think the contact angle hysteresis on copper is a little bit higher than that on the silicon. And I think the main reason is, again, the coating procedure is a evaporation procedure that where wetting plays a big role. So silicon oxide, or the wafers that we use of silicon, they are atomically smooth. They are very, very smooth. Then when we evaporate the coating, the evaporation typically takes place very nicely and homogeneously. Not for the very low viscosity or for the low volume, there are still patches. But if we are going into a copper surface, just taking off the shelf, for example, although it's quite smooth, but still is not sort of mirror finish, it's not so smooth. So in those copper surfaces and also in aluminum, you may get some preferential sites where the oil may pin as it evaporates, and then you will get very, very ununiform coating. But still, we were able to get quite low hysteresis also on the copper and on the aluminum following this procedure. But it's a wetting problem actually. So yeah, all the kind of problems that you may see when you think of wetting, pinning, structure, wettability, they also come into play here, and this is why we wanted to address so many parameters within the study for the fabrication to try to understand better how these play a role. And in occasions, we also, for the fundamental, we also try to minimize other parameters, right? And in this case, one of the parameters we wanted to minimize is the surface roughness.
Okay, we have time for one more question. Otherwise, Deborah has another one, right?
Yes.
What about you?
I have one. I'll finish with mine. Deborah can make her question. I'll finish mine. So we still have time for these two questions, I think. I don't know if anybody.
We did great with the time.
Yeah, I think yes, we are. Congrats. Just sorry. Let me just let.
Yes, sure.
Into.
Please.
The temperature of the evaporation experiments, and you said that you coat and you put in an oven to evaporate.
Sorry. Can you speak a little louder for us, please? Yes.
About the temperature of your tests during the evaporation experiments. So if the coating has some, I don't know, if it changes according to the temperature.
So evaporation experiments, they were done at ambient temperature.
Okay.
Everything at ambient temperature. But that is a good point because of the kind of nature of the silicon. So these typically are called PDMS brushes, grafting. So they are a little bit liquid-like. So the contact line may kind of play a little bit of role on the surface and might change a little bit the kind of surface when as the droplet evaporates. But again, because they are liquid-like, they typically relax and retrieve the same kind of behavior and the same flatness and the same hysteresis as originally. I thought you were going to ask about the whiskey taste because I saw you that you enjoyed that.
So, Deborah, please.
Well, my last question is a little bit aligned to Cristiano's question. Would it be possible, like, to pattern some kind of roughness such that you'd have another or a desirable feature, something like that in the surfaces?
Very good question. So we are not thinking into patterning structures as of now, okay? But during the IHCC International Heat Transfer Conference, because we found that the registration fee was a little bit high, Instead of sending our students to the conference, we actually send them to Pretoria University for a month. And there in Pretoria, they are very applied and they work with copper. So my students were actually were using this procedure for coating the surfaces, but with some surfaces that have been roughened there with either sandpaper or with sort of sandblasting that produce some sort of concentric type of patterns. So we are in the way of processing that data, but we were able to kind of pattern. We were able to make the surfaces hydrophobic, and because of the different structures, instead of having only CCA, constant contact angle or constant contact radius, we also have one of the modes that it appears at the bottom that is called the stick slip behavior because of these structures. With Rice University, we are looking into just patterning different oils, so to try to achieve homogeneous wettability, because you saw independently on the procedure, the wettability is sort of the same, hydrophobic, but we want to make patches of contact angle hysteresis. So what you are mentioning, very interesting, probably very challenging also to kind of achieve because of the sort of preferential attachment of the oil as the contact line recedes and leaves the PDMS brushes on the surface. Probably maybe you get more on the structured surfaces than on the patch surfaces. But yeah, very good point actually. I see you are looking into patterning.
I think we have some discussions with well, just to finish the last question that I have. I had a few, but it's quite simple, I guess, maybe. You always look to reduce the contact angle hysteresis for condensation. That's great. Is there an application that we want to have the highest contact angle hysteresis as possible? What kind of application could you look to do the opposite? Do we have any?
Good question, Arthur. So
because I always see reduction. How about increasing?
So probably if you want to increase and if you want to apply this to sort of heat transfer, probably what we want to be looking at is at sort of the opposite phenomena. We would like to be insulating.
All right, okay.
So
that's
high hysteresis will make bigger droplets or maybe a bigger film. And we know that for heat transfer, for condensation, any type air, liquid, typically the thermal conductivity is always smaller than the solid. So probably what you will be looking at is yes, somewhere where you want to have some insulating properties. Or also in the case of microfluidics applications, sometimes yes, you want low hysteresis for some parts of the chip where you put the droplet and this droplet is gonna go somewhere, but probably in the area where you are doing the test, you want that liquid stays there. So maybe you want to enhance the hysteresis there so that droplet stays there, doesn't go anywhere else, and any of the reactions can happen. So those are a couple of things that I can think of now. Maybe we can discuss more about it.
Okay, let's thank again for inviting. Just also to finish, Leandro, also thank you, our technician, our magician who made the streaming via YouTube. We have about 10 people there watching YouTube, so thank you everybody also online. And thanks, guys. Thank you very much for your presence.
Thank you.